This is the Framework laptop. It's a fully modular, feature-proof laptop that gives you the control to change out any part. For example, need a new battery? Done. Not only that, it features interchangeable ports through the expansion card system, which allows you to customize it to your needs. On paper, this seems like a perfect device, but there's one thing about it that I think I could do better. The keyboard feels like, well, a laptop keyboard. It is by no means bad for what it is, but especially when you're used to things like it's an underwhelming experience to say the least. In this video, I'm going to convert my otherwise typical Framework 13 into a fully custom mechanical laptop. Here's the plan. First, disassemble the Framework laptop. Then, figure out the dimensions of the internal parts, design a new housing for them that features a mechanical keyboard, and finally, drop the parts into the new housing. This video is by no means meant to be a comprehensive guide on how to recreate my project, but rather, simply a documentation of my process that I hope will serve as inspiration for others. This is the making of the campus. Framework makes for an excellent platform to build off of because they are a company that encourages community development. For the Framework 13 specifically, they have provided technical drawings of many of the most important parts of the laptop, including the mainboard, battery, hinges, and display. This made for a super solid starting point for me, as I already had a concrete set of dimensions to start working around. But working with the Framework laptop parts wasn't as simple as I hoped. Their documentation of their parts was still far from complete, which meant for me that I needed to manually measure out more than half of the components with calipers. This was a painstaking process that took me hours per individual part. I noted down all the dimensions on my iPad so that way I could easily refer back to them later. Finally, I had a solid enough collection of drawings that I felt confident to start building up the laptop in Fusion, my CAD program of choice. As with any CAD-based project, I started out the physical design of my laptop by first laying down the dimensions of the most central part, the mainboard. From there, I was able to confidently map out the audio and Wi-Fi modules since they plug directly into the mainboard. Once I was satisfied with the placement of the parts, I started to build up the bottom chassis around them. The Framework laptop chassis is divided into three main parts. The bottom chassis, which acts like a tray for all the major components such as the mainboard and battery, the input cover, where parts such as the keyboard and touchpad are mounted, and finally, the top cover, which is just the lid of the laptop, housing the display and webcam. With the bottom chassis roughly laid out, I also started to work on the input cover. For my design, I essentially wanted to reuse as many parts as possible from the original Framework laptop, except for the keyboard of course. So I started out with working on the fingerprint sensor and the touchpad. These were both parts I had to manually measure myself with calipers, which was very tedious. I used the dimensions I had noted on my iPad to draft the mounting points in my design. Moving on to the keyboard, I decided on using kailh choc switches because I think that they have the best compromise of sound and feel while maintaining a relatively short form factor. They almost have the full travel of a typical Cherry MX switch, but with half the thickness. I made sure to leave a properly sized cutout in the input cover for the keyboard, as well as some mounting points for that. I designed a gasket mounted system which works by simply placing tiny silicone O-rings in between the switch plate standoffs and screws. Having this soft material acting as a buffer between the hard metal chassis and the typing interface ensures a consistent sound and feel across the board, which is a must for any keyboard enthusiast. If you try typing on a newer MacBook, for example, the keys in the center sound vastly different than the keys on the edge of the keyboard. Implementing an enthusiast-grade keyboard into a laptop was something I always dreamed of doing, so this was a refreshing part of the build for me. I also left some holes in the input cover for some rotary encoders, but more on that later. With the foundation of the bottom chassis and input cover completed, I moved on to the lid. At first, when compared to the previous two parts of the chassis, this one seemed more simple. Placing mounting points for the hinges, display, and webcam was all pretty easy compared to the previous parts. But surprisingly for me, the most complexity came with designing the bezel. Originally for the Framework laptop, they designed a bezel that is secured with magnets, making it super easy to take on and off. However, a design like that usually requires specialty injection molding to achieve all of the thin details it has. Because this project is a one-off for me, injection molding is completely out of the question, and I instead went with 3D printing, an economical option for single unit production. However, typical consumer 3D printers are not anywhere near capable of creating the complex features that the original Framework bezel has, so I had to simplify my design to no longer feature the convenient magnets. Instead, my bezel is just a flat surface that will be secured in place using double-sided adhesives, similar to most other consumer electronics out there today. In addition to this, I also omitted Framework's feature of having the privacy switches that physically disable the microphone and webcam hardware, because those were also a little too small for me to 3D print confidently. This was not a big deal breaker for me anyway though. With the foundation of these three main chassis components finished, you can see the whole project coming together, finally starting to resemble a laptop. I did a bit of 3D printing to test fit some of the parts, just to double check I had my dimensions correct. I was also able to mock up the interface to verify that everything was where I wanted it to be. It took a few iterations, but eventually I had all the major details solidified and ready to go. All that was left to do for the physical design was refine the small details before getting the chassis manufactured. I made some simple vents for airflow on the bottom of the laptop. I also made some vents in the rear and embedded the words campus into the grille, which I think was a nice touch. For the interface, I designed some custom knobs around the low-profile EC12 rotary encoders that will sit flush with the surface of the laptop for easy control of volume, brightness, and backlighting. For the finishing touch, I also created a little logo that I embedded into the back of the laptop lid. Finally, when all my chassis parts were completed, I drafted up some technical drawings and sent in my files to get CNC machined. Before I get into the electrical design of my PCBs, I would like to give a quick word from this video sponsor and my PCB manufacturer of choice, JLC PCB. I like their services because their online portal makes it extremely easy to get instant quotes and place orders, and in my personal experience, despite their affordable cost, their quality has been very reliable and their production speed is unmatched. I live in California and I consistently get my PCBs delivered at my doorstep in less than a week after placing the order. Right now, they are having a special for their 6-layer PCBs, which feature free via-in pad, allowing for denser placement of components as well as a premium ENIG finish. Use the link in the description below to get $30 off your first order. JLC has also recently started doing other manufacturing services as well, so I thought this would be a perfect opportunity to try getting my chassis CNC'd through them. They were kind enough to help cover some of the costs for getting my chassis manufactured, so huge shout out to JLC PCB for their financial support. Besides making the entire physical chassis for the campus, my design also warranted 2 custom PCBs. First, similar to many of my previous custom keyboard builds, existing PCBs with the exact combination of layout and features that I'm looking for does not exist yet, meaning that I need to make my own keyboard PCB from scratch. And second, in order to connect the keyboard to the mainboard itself, I also need to create a custom internal USB hub. Making the keyboard PCB follows the same path as any other, where essentially you need to first build up the schematic, making sure you have made all the proper connections for the MCU, USB port, and the switch matrix itself. Once you have all those set up, you can build up the physical layout of the PCB, first making the physical outline, then placing components, then finally routing traces. The whole process is pretty lengthy, but for the sake of time, I will leave it for a different video to comprehensively cover. One tricky consideration about my design was for the rotary encoders. Remember, as I mentioned earlier, the keyboard is gasket mounted with the silicone O-rings. This makes the whole unit a little bit flexible, which is desirable for the keyboard, but not for the encoders, which instead need to be mounted as solid as possible. So I designed my rotary encoder module to break off the main keyboard PCB, which allows the knobs to be solid mounted while keeping the keyboard itself flexible. Once the keyboard was done, I then started to build the USB hub. The original Framework laptop only has 4 interchangeable ports through its expansion card system, which works well for most use cases. But every once in a while, when I want to plug in a bunch of different devices into my laptop, it makes things a little bit more complicated, requiring the use of a USB hub. So for my design, I thought it would be a cool idea to make a USB hub already built into the device in place of one of the expansion card slots. This theoretically should work out nicely since at their core, the expansion card slots are just USB ports. Building the PCB for the USB hub was far more complicated than any keyboard PCB I've ever worked on, since there are a lot of different ICs and components required to get USB communications working correctly. Whereas a keyboard PCB essentially only needs to serve the single purpose of acting as an input device, the USB hub needs to serve many different purposes, not only handling different inputs and outputs, but also converting the USB lines to handle different types of data such as HDMI or SD readers. A single USB-C is capable of handling all of those tasks simultaneously. However, it's not as simple as just a plug-and-play setup. A USB hub is actually a complex network of many different chips and components to make sure data is handled properly. To better explain how the whole thing works, I put together this little diagram showing how the different components interact with each other. Firstly, same as with any other USB hub, it starts with a USB-C input. USB-C natively supports what's called a dual mode, where half of its pins are allocated to a display output and the other half remain for regular USB functionality. But in order to activate this dual mode, a specific chip called a multiplexer, or MUX, is required. From there, this data can properly be split into a display output on one side and a USB on the other side. On the display side, things get a little bit more complicated because USB natively supports a DisplayPort signal, but I would prefer to have an HDMI since it's a more common system that nearly every display is compatible with, whereas DisplayPort is less commonly used. So, in order to get an HDMI signal, a DisplayPort to HDMI converter chip is required. After passing through this chip, we can finally have a proper HDMI signal for use. On the USB input side, coming out of the MUX, we only have a single USB line. If I only wanted functionality for a single port, this would be fine, but since we are trying to make a hub with several different capabilities, we need to use a USB splitter chip that can split our single USB signal into 4 usable lines. From here, 3 of the 4 lines are already usable as is. One for the external USB-A port, one for the internal port where the keyboard will plug into, and one more for an extra internal USB port that I will talk more about later. For the 4th and final USB line, I want to have a micro SD reader since that's something I often use. But similar to how the DisplayPort needed to be converted to HDMI, I also had to use a converter chip to convert the USB signal to an SD signal. And those are all the chips required for data handling, but we're not quite finished yet. These chips all require different voltages to run off of, which further complicates the design. The DisplayPort to HDMI converter chip requires a 5-volt input, which is convenient because USB natively supports 5-volt power, meaning that it can just directly power the chip. But the MUX, USB splitter, and USB to SD converter chip all require a 3.3-volt source, meaning that a voltage step-down converter is required. After passing through this, we can get a proper power source for these chips. Besides handling data and power, each of these chips have specific requirements for other surrounding components, which makes things even more complex than they already are. These include things like decoupling capacitors, crystal oscillators, or various pull-up or pull-down resistors. With all that information down, this is what the USB hub looks like in schematic form. Each of these yellow blocks represents one major component, for example, the USB-C input or the MUX. When all this was completed, I moved on to the physical layout of the PCB. For this part, I worked back and forth between working on the PCB and referencing my CAD design to make sure I was placing everything where they needed to go. One interesting design consideration was this little notch I had to make in order to fit around the standoff for the framework's Wi-Fi board. After many days of hard work, I finished routing everything, and this is what the end result looks like. With the files for both PCBs finished, it's time to order them from a manufacturer to get them into my hands. As I already mentioned earlier, I ordered mine through JLC PCB. Sometime later, after everything was delivered, I had all the parts I needed to put together the laptop, but there was still a bit of prep work I needed to do before assembly. Starting with the CNC chassis, after I unboxed them, I had to tap the threads. I decided not to have JLC tap the threads for me, not only to save a little bit of money, but also because my design required some very shallow holes that required a special tap. Because of the point found on a regular thread tap, you are usually unable to tap threads all the way to the bottom of a hole. To get past this problem, I ground down the tip of my bit, which enabled me to tap the shallower holes. Aluminum, however, is usually not the most ideal material to thread into. Because it is a soft metal, over time you will eventually strip out the threads after screwing and unscrewing into them several times. Because of this problem, I designed a special bracket system that uses 3D printed standoffs and brass heat set inserts that will create a much stronger thread, since brass threads last way longer than aluminum ones. These brackets are implemented across the bottom chassis, which house the components that will most commonly be replaced or upgraded throughout the laptop's lifespan, for example, the mainboard or the battery. After having these brackets 3D printed, I used a soldering iron to install the heat set inserts into the standoffs, then used a high-strength epoxy to permanently attach them, essentially making them an extension of the chassis. I also installed some rubber feet to the bottom to elevate it slightly for airflow. For the finishing touches, I got the campus text laser engraved into the bottom of the laptop, as well as some indicator icons for the volume, brightness, and backlighting knobs. I love how these turned out, and I think it really complements the look of the interface. For the top cover, I made a decal of the campus logo and had it cut out of vinyl on my friend's Cricut cutter. When I applied it to the recess on the lid, it really gives a nice finished look. With these parts done, the aluminum chassis parts were all ready to go. Moving on to preparing the PCBs, there was also a little bit of assembly work needed for those as well. For the USB hub, this meant soldering the different ports including the USB-C, HDMI, USB-A's, and micro SD reader. The USB hub also acts as the bridge between the mainboard and the keyboard, with a plug that connects to the keyboard PCB. For the keyboard PCB, all the physical prep work I needed to do was just to solder some jumper wires between the main keyboard module and the rotary encoder module, so that way they would be connected even though they are mounted differently from each other. Whenever you make your own custom keyboard PCB, you also need to build your firmware yourself as well. Most standard wired keyboard PCBs are going to be based off of QMK, the most common custom keyboard firmware. For this video, I'm not going to cover the process in too much depth, since building the firmware has many small nuances that other creators have already covered in much more detail than I can. Normally, it's a good idea to create your keyboard firmware from complete scratch, but in my case, I was able to simply copy my firmware files from my previous project, the Summit, since it nearly shares the same layout as this project. There were just a few different things I needed to configure, such as the rotary encoders, but it all came together very quickly. Once the firmware was all set up, I flashed it onto the keyboard PCB. Putting together the keyboard itself followed the same typical build process as any other custom mechanical keyboard. For this build, I used kailh choc sunset switches lubed with Krytox 205 grade 0. Even though I've built more keyboards than I can count in the past, this was actually my first time ever doing a build with low profile switches, and I was pleasantly surprised with how nice the choc sunsets feel. They have a medium light tactile bump, which is right where my preferences are for a daily driver. To improve the stabilizers, I did an old modification called the Holy mod on them, which involves cutting a small strip of Band-Aid and sticking it to the inside of the hole on the stabilizer stem. This eliminates any ticking you might get from the wire tapping against the plastic housing when pressing the key down. I had good success with this mod in the past with old Cherry plate mount stabilizers, so I figured I'd give it a try for the choc stabilizers as well, since they are also plate mounted with a similar mechanism. After installing them and testing them out with some switches, I was very satisfied with how they turned out. After that, the rest of the keyboard build was as simple as popping in the rest of the switches and soldering in the pins. Besides that, I also soldered the rotary encoders onto their respective pads. With both the CNC parts and the PCBs all prepared, it's finally time to put the laptop together. I began with transferring the bottom chassis parts from the framework laptop. Starting with the mainboard, I directly plugged in my custom USB hub, which makes them essentially function together as a single unit. If you remember the extra internal USB port I mentioned earlier, this is where it comes into play. Ideally, if you have a wireless mouse that requires a dongle, you would be able to plug it into this concealed port without needing to sacrifice an external slot for it. I thought this was a really cool feature to implement, and because I was designing my own USB hub entirely from scratch, it wasn't significantly more work to implement. After that, I transferred the battery, as well as the audio board and Wi-Fi board. That's pretty much all for the bottom chassis, so now let's move on to assemble the input cover. I started with transferring the fingerprint reader and touchpad, since they were just direct drop-in replacements. Then, I installed my custom knobs onto the rotary encoders, securing them with set screws. After that, the keyboard and encoder modules could finally be mounted to the cover. The encoder module is simply screwed down to the standoffs, but for the keyboard module, all the hard parts are individually spaced out with tiny silicone O-rings. One thing I had to make a major redesign for was the speaker placement. Originally on the framework laptop, the speakers are placed in a vertical orientation facing down. But because I wanted the rotary encoders along the same edge that the speakers normally are placed, this caused a conflict. My solution to this problem was to instead place the speakers in a horizontal orientation, mounted to the input cover instead of the bottom. This updated orientation only works because of how much space my design has above the battery. I ended up needing to splice in some extensions into the speaker cables because of this alternate position, but this process went smoothly with no hiccups. With all this done, the input cover was finished, so it's time to move on to the final part, the top cover. The top cover was relatively simple, since there weren't as many parts that needed to go into it. I started with mounting the hinges, then installed the webcam module. Interestingly, after taking apart the framework laptop, I found that the entire body of the lid functions as the Wi-Fi antenna, and it works by having these conductive pads stick to some exposed aluminum, with wires running down to the Wi-Fi board. I replicated this in my design as well. After that, the last part to install was the display. With everything in place, all that was left to do was install the bezel. Mine was fully functional straight off the 3D printer, but I wanted to make it look a little bit nicer before installing it. I sanded it down with some 220 grit sandpaper, then used some filler putty to smooth out all the micro crevices you get from the 3D printer. Then I primed it, wet sanded it some more, and finally painted it gloss black. To add a bit of durability, I added a few coats of clear on top. After that, I just used some thin double-sided tape to mount the bezel in place. That marks the finish of all three chassis parts. The bottom chassis, which houses all the primary components like the mainboard and battery. The input cover, which hold together the parts you interact with, such as the keyboard and touchpad. And the top cover, where the display is. Now I can finally put together all the parts for the final assembly. I began by attaching the top cover to the bottom chassis. This is done with just 2 screws for each side to mount the hinges. With the lid attached, I plugged in the cables for the display, Wi-Fi, and webcam modules into the mainboard. Then I plugged in the cables for the input cover. First, the speaker cables that I extended and touchpad cables get plugged into the mainboard. Then, the keyboard cable gets plugged into the USB hub. After that, all that's left to do is install the 5 screws in the bottom, and the laptop should now be fully functional. The finishing touch of any custom keyboard build is always putting on the keycaps, so I thought it was fitting to save it for last for the campus as well. I'm using MBK profile keycaps since I like their quality and I think that they're one of the best options out there for kailh choc switches. I actually had to combine 2 different keycap sets just for this laptop because most low profile keycap sets are designed for ortholinear or other ergonomic boards, which do not often use the modifier keycap sizes found on standard keyboards, as well as a full-size spacebar. At the time of recording, only MBK colors had the full set I was looking for, but the problem was that it only came with blanks, and after daily driving a blank keyboard for a few months, that's not something I would want to go back to. So I combined the modifiers from MBK colors with the alphas of MBK legends. Besides that, I also wanted to have some accent colors as part of the keycap set. I'm a really big fan of vintage HHKB builds, and I've always loved the PFU colored accents for the control and escape keys. Because my keycaps are made of PBT, they are compatible with polymer dies. Specifically, a brand called iDye Poly is known to work well within the keyboard community. I had success using this dye in one of my earliest keyboard builds, so I went ahead with using it again for this one. I dyed my control and escape keys orange not only to have a little extra pop of color on my keyboard, but also as a subtle reference back to the original PFU HHKBs. This turned out to be the best solution I could piece together without having to commission a one-off keycap set, which could get really expensive. Finally, the campus is complete. I'm really proud of how it turned out, and I'm especially happy about how I was able to retain the features that made me fall in love with the original framework laptop. Having the interchangeable slots, extremely simple disassembly, and modular internals are all features that I wish all laptops had. Besides that, I was successful in adding my own flair to the design, with the integration of a mechanical keyboard, rotary encoders for volume and brightness control, and many other small details found not only on the outside but also on the inside of the laptop. I was able to get everything fully functional for the most part, and as a matter of fact, I even edited this video using it. As with every first iteration of a project though, I know it's far from perfect. I ran into many different roadblocks and issues throughout the process that were impossible to anticipate, and overcoming them was a huge learning experience for me. One of the biggest problems that I ran into was that I unfortunately was not able to get the USB hub working properly. I think the complexity of the connections were a little bit too advanced for my current skills, and somewhere down the line I'm pretty sure I made a small mistake causing it to not even be recognized by Windows entirely. This was pretty disappointing for me since that meant I wouldn't be able to use the HDMI port or SD card reader, as well as the internal slot for the wireless dongles. This is one of the trickiest parts about PCB design. Unless you already know what you're doing, there's no way to know if your design is going to work until you actually spend the money to get them manufactured. For the sake of finishing this project, I was able to get the keyboard and encoders working by plugging them in through a daughter board to completely bypass the non-functioning USB hub, but at the cost of the ports not working. But the other 3 interchangeable ports all work fine, so the laptop is still by all means usable with just those. Another issue I ran into was that for some reason, even though I did my best to replicate the framework Wi-Fi antennas by wiring directly into the lid, though it technically works, my Wi-Fi reception turned out very weak. Again, it's just a minor inconvenience though. These are the 2 biggest issues I ran into after completing the project, but they aren't complete deal breakers to me. I'm still going to enjoy using this machine for years to come, and maybe eventually I'll get around to troubleshooting out the issues to bring back full functionality of the USB hub. At the end of the day, I'm still extremely happy with my results, and even though there are things that can be improved here and there, I'm still satisfied with what I was able to accomplish. There were no doubt challenging problems throughout the process, but I found overcoming these problems to be the most gratifying parts of the project. If everything was easy and smooth sailing the whole way through, where's the fun in that? If you've made it this far with me, I'm sure by now you're all curious to hear how the campus sounds. So without further ado, here's the typing test, and thanks for watching.